Hi guys, Mr. Kane here. I want to talk to you today about using ice tables. Basically, it's a method. In chemistry of using logic and mathematics along with your problem solving. It's really helpful with problems that have equilibrium. Okay, so we're going to dive right in here. What you should see is that an ice table talks about initial, change, and equilibrium portions of a particular reaction. Okay, so that's ICE, initial, change, and equilibrium. You'll notice that we've been given a balanced chemical reaction and that we've been given some details about this reaction. It says that we've got a reaction that's got a mixture that contains 2 molar N2, 2 molar H2 at the initial. It says that at equilibrium, the concentration of NH3 is 0.850 molar. It's asking us to calculate the K of this particular reaction. Okay, so here's how we use an ice table to help us out with this. We know that K is going to be products over reactants. So it's going to be NH3, concentration of NH3, squared over N2, concentration times the concentration of H2. And H2 has to be cubed. Remember, we're getting these squared and cubed terms from the balanced chemical reaction. This one gets no exponent because it has no coefficient. It's a coefficient of 1. I'm going to plug in N2 in this part. I'm going to plug in H2 here, and I'm going to plug NH3 in here. I'm going to fill out the parts that I actually know. For instance, the I know that initial, I have a 2 molar solution of N2. I also know that I have a 2 molar solution of H2, and it doesn't say anything about the NH3. I'm going to assume, since it doesn't say anything, that I've got no NH3 at all. Okay. They do tell me that eventually the equilibrium concentration, so equilibrium, I skip my C row and I go to my E row, equilibrium concentration of NH3 is 0.850 molar. They want me to calculate the K. In order to calculate K, I'm going to need to know both of these concentrations and plug them into the equation on the right. That means that the next thing I have to do is figure out what my changes are going to be. So this reaction starts out with all reactants. It's going to start making products, which means I'm going to lose reactants. I'm going to lose a certain amount of reactant on this side. I'm going to call it X. Okay. I'm also going to lose a certain amount of this reactant, the hydrogen. It turns out that there's a relationship between these two reactants. It turns out it's a 1:3 ratio. The same ratio that's found in the balanced equation. So that means that if I lose X amount of N2, I'm going to lose 3 times that amount of H2. What's going to happen to NH3 is that I'm going to gain 2 times that amount of NH3. Okay. What that means is that I can write in these terms. I can write that my N2 at the end is going to be 2 minus X molarity. My H2 is going to be 2 minus 3X for molarity. And my NH3 is already given as 0.850. But I said that that was changing by 2X. So this is a relatively simple problem. I'm seeing that 2X is the same thing as 0.850 molar. If I divide both sides by 2, I find out that X is going to be equal to 0.425 molarity. Okay. What that means is that N2 is going to be 2 minus 0.425, which is going to be 1.575, but with sig figs, I'm going to call it 1.58 molarity. And my H2 is going to be 2.00 minus 3x. Well, that's 3 times 0.425. And that is going to wind up being 0.725 molar. That means that when I come back up here, I can plug in NH3. NH3 is 0.850 molar. My N2 is 1.58. And my H2 is 0.725. Now I forgot about some key items here. This term has to be cubed and that term has to be squared. I need to plug this into my calculator properly so that it takes care of order of operations for me. Usually what that means is me putting a parenthesis around the denominator. If you've plugged this into your calculator properly, you wind up finding out the K of this reaction is going to wind up being 1.41. That's 3 sig figs. Notice no units on K, and this is only a somewhat favorable reaction because it is making a little bit of product compared to reactant, but not a heck of a lot more. They're starting with a reactant of NH3, and N2 and H2 wind up being products. They say that the reaction mixture initially contains 0.750 molar solution of NH3. At equilibrium, we've got an N2 concentration of 0.300 molar. They ask us to calculate the equilibrium concentration of NH3, of H2, and they're also asking us to find what the K value is in this case. Since the reaction is actually flipped, that means that the concentration of NH3 winds up on the bottom this time, being squared, of course, and that the concentration of nitrogen is at the top, along with the concentration of hydrogen, which is cubed. Looking at my problem here, it appears to me that this reaction is going to be proceeding to the right, which means I'll be decreasing by 2x for NH3. I'll be increasing by x for N2, and I'll be increasing by 3 times x for H2. Again, I'm assuming that I've got no nitrogen and no hydrogen since they didn't tell me about it. It looks to me like I already know what x is. X is 0.3. That means that 3 times x is 0.900 molar. That means that 2x would be, well, 2x would be 0.6. And so basically I'm taking 0.750 and I'm subtracting 0.600. So that's 0.150 molar. So I've solved for my concentrations. Those are written down already. I just have to finish up the problem by calculating the actual K value. N2 is going to be 0.300 at equilibrium. The H2 at equilibrium is 0.900 cubed. And NH3 squared is 0.150 squared. Okay, plugging these into my calculator, it's 0.300 times 0.729. I'm dividing by 0.0225. What we're finding out here, after we plug that into our calculator, is that K winds up having a 9.72 value. This is fairly favorable. We're getting about 10 times more product than we are reactant. So here's a different problem. Here we've got hydrogen, we've got bromine, and we've got hydrobromic acid. We've got a weak acid here. It actually says that we got 2.53 grams of hydrogen and 200 grams of bromine placed in a 450 milliliter reaction vessel. We don't really want to use masses in our in our ice table here. We want to use moles or molarity. I prefer to use molarity. So here's what we're going to do. First thing we have to do is we have to take our 2.53 grams of hydrogen and we have to divide by the molar mass to get the moles. It turns out that we have about 1.25 moles of hydrogen sitting here, and I should make a note that this is a hydrogen calculation. Bromine, on the other hand, we've got 200 grams of, and the molar mass of bromine is 159.8 grams. And it turns out that this is 1.25 moles of bromine as well. We're placing these 1.25 moles in a 0.450 liter reaction vessel. So I'm going to divide by 0.450 liters on both of these problems. And you can see that they're the same problem. So essentially both molarities wind up being 2.78 molar, regardless of the fact that we started with different masses. So I'm going to slide over here and I'm going to write that in as my initial concentration of hydrogen and bromine. The next step is going to be to calculate out the equilibrium concentration of HBr. That's all we really care about here. I am going to be losing X of hydrogen, losing X of bromine, and adding in 2 times as much HBr. That means that this problem is going to wind up being 2.78 minus X, and this problem is going to be 2.78 minus X. And this is just going to be 2X at the end. Question is, what's the value of 2X? Well, we're going to have to plug into the K in order to find this out. So we know that the K should be, oops, this equation is not balanced. I'm going to put a 2 right there, coefficient, because I'm noticing that that's going to be important. The concentration of HBr is going to be squared. Hydrogen and bromine don't have exponents because their coefficients are 1 in the balanced chemical reaction. So let's see what we can replace with numbers here. K is 450. HBr I'm going to replace with 2X. And remember that 2X winds up being squared, the whole quantity. And then we wind up with 2.78 minus X times 2.78 minus X. Okay. Now you might look at this and your eyes might start crossing. We got things where we're going to have X's being squared and X's being single. I think we can actually use a little math trick here. If I take the square root of the entire right side, that's going to get rid of this squared term here. And since in the denominator we're multiplying the same term by the same term, I'm going to get rid of one of them. Okay, that's going to mean that we have 450 going to be equal to 2X over 2.78 minus X. Okay, all right. So I'm going to get the 2.78 minus X. I'm going to multiply it on both sides. So that's, I get 1,251 minus 450X is equal to 2X. Then I'm going to add the 450X to both sides. So that I wind up with 1,251 is equal to 452X. We're going to divide both sides by 452. So X is equal to 2.77 after we calculate that. Okay, this reaction is going to require that we have nitrogen monoxide, nitrogen gas, and oxygen gas being used. We're given the K value is 2.40 times 10 to the third, and we're going to set that equal to our terms. They tell us that NO starts out as 0.200 molar, and they don't tell us anything about nitrogen or oxygen, so we're assuming 0. So according to our balanced equation, we should be adding X of nitrogen, we should be adding X of oxygen, and we'll be removing 2X of nitrogen monoxide. That means that NO is going to be worth 0.200 minus 2X. This is going to be worth X for nitrogen and also X for oxygen. Okay. That means I've got an X squared term up on top because essentially it's nitrogen times oxygen. X times X is X squared. And on the bottom I'm going to wind up with 0.200 minus 2X. I'm going to cross multiply here to get things all into numerators. So we're going to wind up with X squared being equal to, and on the other side, I'm going to get 2.40 times 10 to the third times 0.2, which is going to wind up being 480. And I'm going to subtract from that 2.40 times 10 to the third times 2, which is basically 4,800. X. Now, to solve this, we're going to want to put it in standard form. So I'm going to subtract X squared on both sides. That's going to give us 0 is equal to 480 minus 4,800X minus X squared. Now, those of you who really enjoy math class might remember that we could use the quadratic formula, negative b plus or minus square root of b squared minus 4ac over 2 all over 2a. Others of us just appreciate making this a little easier. So what we're going to do is we're going to find a quadratic equation solver. Graphing calculators have a quadratic equation solver that you can use. Or you could go to mathisfun.com/quadratic-equation-solver.html. I'll provide a link for this. A term is our X squared term. So as you recall, that was just minus X squared. So I'm just going to put in a minus 1. Our B term was our 4,800X. And that was also negative. So I'm going to put a negative sign in front of it. And our C term was positive. It was 480. What's been determined here is this. There are two possible solutions to the problem. One of the solutions is 4,800, but it's a negative value. That makes no sense for us in terms of our ICE table because that means our concentrations will be extremely negative, an impossible situation. The other solution to the quadratic is that our final answer is 0.099. So I'm going to come back to our work here. So I'm going to make a note here that X was 0.099. That was our solution. So that means that the molarity of O2 is going to be 0.099 molar. That N2 is going to be 0.099 molar. And that nitrogen monoxide is going to be 0.200 minus 2 times 0.099, which is going to come up with a fact of 0.002 molarity. So here with this last problem, it's going to be another situation where we're not going to solve quite the same way. Notice that in this situation we got hydrogen gas, we've got bromine, and we've also got HBr. So we've got this weak acid, hydrobromic acid. They tell us that we're starting with initial concentrations of 0.485 molar, 0.261 molar for bromine, and 0.399 molar for the HBr. The thing that's they're asking us to solve for here is the equilibrium concentration of HBr. So we're trying to solve for this. We know that the K is equal to 0.500 here. Okay. Before we can even begin to solve this problem, though, we need to fill in our change. We need to know our plus x's and our minus x's. But the problem is we don't know which direction this reaction's going. The other reactions have started with a certain amount of reactant, but no product. So we know it was going to move towards the right, which means that we would be adding product and decreasing reactant. So here is where we have to use Q and employ that. So the first thing we're going to have to do is calculate what Q is. So Q is going to be calculated the same way that KEQ would have been calculated. We're going to take our 0.399 and we're going to put it on the top here. We're going to square it. The hydrogen was 0.485. And we're going to multiply that by the 0.261 that was bromine. That math is going to wind up getting us a Q of 2.593. So I'm going to say 2.59 here. Okay. Now what we want to do is we want to compare our Q to our KEQ. It looks to me like our Q is 2.59 and our K is 0.500. That means that Q is going to be greater than K. That means that this reaction has too many products to start with, and it's got products that it doesn't want. It's going to wind up shifting this reaction to the left. So what that means is that as I proceed to solve this problem, I now know that I'm going to be adding reactants, and I'll be subtracting products. Okay. Now, as we continue our thought process here, we're going to get 0.485 plus x, and we're going to get 0.261 plus x. We'll get 0.399 minus 2x. As we plug in to our KEQ, one of the things that we're going to realize is that this problem is going to be complex. It's going to require using the quadratic. And it's going to take up several more minutes. I'm not going to finish up the video by showing all of the calculations here. Instead, I'm going to suggest this. I'm going to suggest that when we plug into the quadratic equation solver, we're going to get 4 values. 2 of them are going to be imaginary values. They're going to have i's after them. One of them is going to be negative, and one of them is going to be positive. The positive value is the only reasonable value here. So x is going to come out to be about 0.0760. If you follow that through, ultimately SO3, if you want to check your work on it, is going to come out to be 0.247 molar. Okay. Hope this helped out a little bit.